of change of a covariant basis element, if you just imagine what happens to S1, let's look at ds1, ds1. So it's the rate of change of the first basis vector with respect to the first coordinate. Right? As you can see, it'll curve with the surface. And when it curves with the surface, its rate of change will not lie in a tangential place. We'll have a component normal to the surface. I think it's quite apparent. It will slightly in that direction. Because that's the direction in which this vector is changing. It's making more and more of that direction curves. So this derivative lies in the overall landing space. It does not lie in the tangent plane. And it is therefore not possible to decompose it with respect to the covariant basis, which is only capable of expressing vectors that lie in the tangential plane. So this definition is not possible, and the cause of this state of affairs is curvature. So this actually is a very positive step. It gives us a handle on the concept of curvature. So I'm going to erase the board and show you how to fix this problem, which is done in there are two ways of doing it. They're completely equivalent. And both of them will lead to the concept of curvature. I'll show you one and show you the other. But for now, let me box this and cross it out so that this is captured on video. Okay, we're back, and you will recall an expression similar to this one in Euclidean spaces. I'm not sure if I've ever written on the board, but it's certainly very prominent in the book. We don't emphasize it early on to show it as one of the interesting consequences of the primary definition that we use, the one that doesn't work on surfaces. But a definition such as this of the Christoffel symbol is actually very important. It shows its intrinsic nature. It shows that if we know the metric tensor and how the metric tensor changes from one point to another, which is captured by these partial derivatives, then we actually have the Christoffel symbol. That means that the Christoffel symbol can actually be defined strictly in terms of the covariant derivatives. The derivatives of the covariant metric tensor. That's actually very important. It's one of the ways to save the situation in our case right now. So our definition that we attempted here through the vectors didn't work, but we have the metric tensor, and we therefore have this definition. And remember what we want the Christoffel symbols for. We need the Christoffel symbols primarily in order to define the covariant derivative. And for the covariant derivative to have the tensor property, in other words, to produce the tensor output for tensor inputs, we only need a symbol, such as the Christoffel symbol, that changes according to a certain rule under change of coordinates. And the symbol defined in this way will change according to the right way, in order to the way that would lead to a great covariant derivative. So on the surface, by analogy, or actually in any space, or any manifold, in which the metric tensor is defined the way we did it, or arbitrarily given a priori, if you write down a definition like this, you will have an object that changes according to the way you want from one coordinate system to the other. And it therefore can be used in the definition of the covariant derivative, and everything's great. So this is one of the ways, the intrinsic way of introducing the Christoffel symbol, and it works just fine. However, we don't want to quite give up on our extrinsic approach that uses the covariant basis, because it's a very geometrically intuitive and very visual object. We don't want to give up our geometric intuition just yet, and we really want to be able to use and work with the covariant basis, because it's such a great object. So I will now write down what previously was used as a consequence of the definition of the Christoffel symbol, but it will now serve as the definition of the Christoffel symbol. And it is this. Alpha, beta is this dot product. But remember before, it followed from this definition by dotting both sides with the contravariant basis element. And these were the explicit components of this object with respect to this object. Now it can no longer be interpreted as the explicit components of this object with respect to the contravariant basis, because this object cannot be decomposed with respect to the covariant basis. However, it's still 8 numbers, and because it has this form, the same form as in the Euclidean space, of course it will change by not necessarily the same rule, but a completely analogous rule to the way it changed in the Euclidean spaces. Because this can be taken as the definition in both cases, and then all of the analysis would be the same, and the rule by which this symbol is changing, actually that was one of the topics that I'm planning on backfilling. Today is April 21st, so if you're watching this a month or so from now, it's probably backfilled already, and you've seen it. If you're watching it shortly after I uploaded this, then you might not have seen it, but of course it's all over the book. Okay. So this changes according to the rule that we want, and we can therefore use this object to define the covariant derivative, which is defined by the exact same rule as before. It's the partial derivative plus the Christoffel adjustment term for each of the indices of the object. Alright, so now let's assume that the Christoffel symbol has been defined and that the covariant derivative has been defined. And that's now, because it's defined by the symbol, that's now studying the properties of the covariant derivative. So it's a big jump, but it's fair because it's exactly analogous. So you can review those lectures and replace z's with s's and in Latin indices with Greek indices, and everything will work the same. Except one thing, and that's the one thing we'll concentrate on right now. Let's talk about the metronylic property as applied to the covariant basis. Okay. So here's the big question. What is the covariant derivative on the surface, the covariant surface derivative of the covariant basis? In the Euclidean space, in the ambient space, this was 9 zeros. That was the metronylic, one of the elements of the metronylic property of the covariant derivative. The covariant derivative applied to the covariant basis and the contravariant basis is 0. Or a lot of zeros. In this case, it would have been 9 zeros. But here we have 4 vectors. And we should have some doubt as to whether or not this would be 0, because after all, these guys do curve. And because this is designed to capture the rate of change of this vector, because they do curve, maybe we won't quite get 0. Okay. I realize now I should have left a little bit more space here. You'll see in a moment why. So let's write down this definition. So we have d, by definition, it's ds beta, ds alpha, minus, because it's a covariant type thing, minus gamma, alpha, beta, omega, I will use here, s, omega. Okay, is this 0? Well, we're not sure. Previously, we concluded that in the Euclidean space, that this expression was 0 was a very easy conclusion, because this term was exactly this term, because this term was merely the decomposition of this term with respect to the covariant basis. So at this point, we're observed that this expression is easily seen to be 0, and that was that. Now we have this definition of the Christoffel symbol. We've had to give up, it's not up to us, that this object can no longer be decomposed with respect to this basis. So none of these 4 vectors can be decomposed with respect to the covariant basis. So we can no longer conclude that this is 0. In fact, it's not. But let's see what we could conclude. Let's dot both sides of this expression. I'll use yellow chalk so you see the contrast with a member of the contravariant basis. So I want to dot both sides of this expression. Find S gamma. Dot this. Dot this. Alright, now we have 0. Can you see that? That this expression is 0? Why? Because this right here is delta gamma omega. So contracted with the Christoffel symbol, we'll replace omega with gamma. So this is gamma alpha beta. And this is gamma alpha beta by this very definition. Now it seems to me that alpha and beta are switched, but of course this is symmetric with respect to alpha and beta. It's a very important exercise to prove that this object, even though it doesn't appear from being written in this way, that it's symmetric with respect to alpha and beta. But it is actually true, and very important for you to see why. So